All right. Our next speaker is Takemasa Masuda from Japan Synchrotron Radiation Research Institute, Controls and Computing Division. Takemasa is a researcher in accelerator controls at SPring-8, mainly in charge of hardware and software for equipment control. He's able to talk about porting the VME-Based Optical-Link remote I/O module to your PLC platform.
Okay. Thank you, Chairman, and good morning, everyone. Let's start my presentation. The title is Porting VME-Based Optical-Link Remote I/O Module to a PLC platform. Okay. This is outline of my talk. At first, I'll mention about our background of this development, a new master module for optical-link remote I/O system. Then, next, about our development, including our design policy and the implementation of hardware, software, and FPGA logic. And finally, I'll summarize of my talk. So in SPring-8, many VME computers are employed as front-end computers. And a lot of optical-link remote I/O systems are utilized to cover widely distributed accelerator equipment effectively. And this system consists of VME-based master boards and several kinds of slave boards. And we have mainly two types of optical-link remote I/O system. One is a system called RIO, and the other is called OptVME. The RIO system, these pictures so, and was developed by the company, and the system was used for 20 years. And we have employed over 1,400 slave boards in SPring-8. But unfortunately, this module was discontinued already. However, many of them can be replaced with the other optical-link remote I/O system of the VME, because we have prepared the compatible slave boards. So OptVME system was developed by SPring-8, and there are two types of VME master boards available. One is this picture, OptVME, and the other is OptCC. OptCC has a 12 channel with dual slot. And we have employed over 400 slave boards in SPring-8. The communication protocol between the master and the slave is also developed by SPring-8. This protocol only supports point-to-point connection. And for our convenience, OptCC is also available in the relay mode like this. So the maximum 132 slave boards can be controlled from a master. It is realized by switching control interface from VME bus to the dedicated optical link channels. So the communication procedure with the remote slave board is implemented in the device driver for the master board. Because the protocol is not supported this type of connection. So the device driver is responsible for the high-level communication procedures, including the remote slave control. So moving on the platform consideration, VME has been passed over 30 years, and it already become out of date. I think the VME has two major issues. One is a lack of bandwidth. The other is that the de facto standard bus split chip TSI-148 was already discontinued. So this has been the big problem for VME users, of course, including the SPring-8. So I'm very interested in the next presentation by Greg. He proposed some solution. Okay. Anyway, we have been considering the next generation alternative platform. So as a high-end platform, we have decided to introduce MicroTC804. At present, analog-based old low-level RF system controlled by the VME is planned to be replaced with MicroTC804-based digital one. Meanwhile, to cover a low-end side, we consider Linux PLC like ERT3, FM3 by Yokogawa Electric Corporation is one of the candidates because it has been already applied as a front-end computers in SPring-8. And so in order to effectively utilize the resources of large amount of OptVME thread boards, we have developed the new master module of the OptVME system based on the ERT3 platform. So in this development, we take into account of alternative platform portability, such as PCI Express. So this picture shows a new master module called OptPLC. The dimension of the module are shown here, and the main specification of this module are listed here. Okay. And our design policies follows. Equip the module with as many optical channels as possible, and separate an I/O unit from a logic control unit to keep the expandability of the logic control unit, and control the module using the ERT3 platform general purpose device driver to avoid newly developing and supporting the dedicated special device driver. And finally, control the module from the Sequence CPU in addition to the Linux CPU. About this, today I don't mention. Policies 1 and policies 2 are achieved by hardware implementation. This module consists of 3 PCBs. One is a control logic board, and the others are I/O boards with totally 5 optical channels. Actually, we would like to use a FMC connector to connecting these modules, but the PCB size is a little bit small, so we gave up to mount the FMC. Okay. So about policy 3 was realized by implementation of software and FPGA logic. The keyword is SoC. An ERT3 general purpose device driver is supplied and supported by the company, and it is a very primitive device driver to handle memory access and interrupt. On the other hand, please remember that the device driver for the this master module is responsible for the high-level communication procedures. So the problem is how and where do we implement these high-level communication procedures? So we adopt SoC. We have implemented the high-level communication procedures written in the device driver here as an application software running on ARM Linux in SoC. And the sequence control code and the parameters, which are arguments of octal system call, are set into the dedicated dual port RAM area to pass the communication procedure process. And communication procedure process receives the request code to determine the execution procedure. And we And then we use the general purpose device driver here. And as a result, the device driver or platform side is simplified. The module portability to other platform is enhanced. So this is an implementation of FPGA logic. Here is a PS part of ARM Linux, ARM CPU. And we prepare the two local bus to interface with control logic here. And by replacing bus interface here to the PLC bus, we can port the FPGA logic, control logic to other alternative bus. Okay, I'll summarize my talk. We have successfully ported the VME-based optical-link remote out system I/O module to the ERTC platform. The development module of the PLC is equipped with Sync SoC to build the communication procedure as an application software on ARM Linux. So we can port the developed FPGA logic to an alternative bus, for example, the PCI Express, by replacing the PLC bus interface block in the PL part. And the interface simplification enhances the module and the logic portability. Okay, that's it. Thank you for your attention.
Thank you very much. We have time for a couple of questions. Are there?
I have a question.
Yes?
Yeah.
So, your decision to move away from VME to either micro-TCA.4 or PLC, is it a general decision, or it only applies to this particular case? And if you have made a general decision, will you phase out VME quickly, or will you just not have any new developments with VME?
Maybe I think we have a lot of VME computers, actually. So all of the VME computers dropped is difficult. So it was difficult. So many of them are still remain in the future. I think so, yeah.